This is ZyCodes, and today I'll be building my rendering system from scratch. By the end of this video, I'll be able to upload an image file and render it in my window. I hope you enjoy the video and learn something along the way. So with that, let's get started. The first thing I want to talk about in this video is how a rendering system works. There are three classes you need for a rendering system: a texture, a shader, and a renderer. So a texture class is responsible for loading, formatting, and storing an image file that you want to use. The texture class decodes the image into pixel data and stores it in CPU memory. It then uploads this data to the GPU so it's able to be rendered. The shader class is responsible for loading, compiling, and linking your GLSL shaders. Shaders are small programs that run on your GPU that tell it how to render something. Your shader class takes your shader files, makes them into a readable program for the GPU, and allows you to use them for rendering. Now your renderer uploads data for each vertex to the GPU, binds the texture and shader, and issues the draw call. Basically, your renderer ties everything together and actually allows you to make something show up on your window. Okay, so the next thing you need to do to render is write shaders. Your shader class compiles these shaders, but first you need to write them. Shaders are written using GLSL, or OpenGL shading language, and they're basically the instructions to the GPU, just like how Java is instructions to the CPU. Now there are two types of shaders, vertex and fragment. Vertex shaders run once for each vertex. They take in the vertex data, which is just the information about each corner of the quad. For each vertex, you need to know the position, which is where the vertex is on your screen, and the texture coordinates, which is the corner of the image each vertex corresponds to. Vertex shaders also apply transformations that you need, like moving, scaling, or rotating your image. Essentially, it takes your original vertices and changes them to the final positions the GPU will use. Finally, the vertex shader passes its data to the fragment shader. The fragment shader runs once for every pixel you are rendering. It determines what color every pixel should be. Basically, the fragment shader takes in the texture you sampled, figures out where the pixel it's rendering maps to your texture, and outputs that color to the GPU. The fragment shader is also in charge of applying effects like tinting or transparency. The last thing I want to talk about is just the full process, the order everything happens. So the first thing that happens is you make a render object and call the render method. When your render is created, it creates a shader object which compiles your GLSL shaders. The renderer binds this program, which gives the GPU the vertex and fragment shaders. The renderer then binds the texture, which gives the GPU the image it's going to sample from. Next, the renderer uploads the vertex data to the GPU, the position, texture coordinates, and anything else you need. And at this point, the GPU has everything it needs to render. The GPU then runs the vertex shader, once per vertex, and the GPU now knows where the quad will appear on your window. The GPU runs the fragment shader, once per pixel of the quad, and the GPU knows what every pixel will look like. Finally, after both shader runs, the GPU will draw each pixel on the screen, and you'll have a rendered image on your window. Now this is a very simplified explanation of everything, so I do encourage you to do more research if you're interested in the topic. Now let's move into the code, and I'll show you a few things I think are important to remember. First, in the texture class, if you're making a pixel art game like me, make sure to use GL_nearest instead of GL_linear when you're writing the min and mag filters. GL_linear averages the pixels around it, so it'll make the pixels blur at the edges, while GL_nearest just uses the closest pixel so it makes nice, crisp images. The only other thing in this class I want to point out is that you might have to include the line S2BI set flip vertically on load. Depending on how you set up your texture coordinates, the image might map upside down, so including this line will flip it vertically when you load it, but in my case, I don't need it. Now in your shader class, remember that you need to be able to take in both a vertex and a fragment shader, be able to compile them both, and link them. You will also need methods to upload data to the uniforms in your shaders. Since I have a mat4 and a sampler 2D uniform in my shaders, I'll need an upload mat4f and an upload int method to be able to get the data into the shaders. And again, I don't have that much experience with LWJGL, and I'm doing this project to learn, so I don't fully understand how to write these shaders. I definitely used outside resources, I looked at documentation and watched tutorials, and I encourage you to do the same. I'd also encourage you to try to make it your own, although I admit there's not much to change in the shader this short and simple. But finally, in your renderer, I want to explain VAO, VBO, and EBO. VAO stands for Vertex Array Object, and this is basically just telling you the outline for your vertices, telling the program which vertex attributes exist and where they are in the array. That's what you're setting down here with the GL vertex attribute pointer method. It's telling you where and what each attribute of your vertex is. Now VBO means vertex buffer object. This is just the actual vertex data that's stored in GPU memory. And your EBO is your element buffer object, which stores the indices that determine what vertices to use and in what order when drawing. Then inside your render function, you need to bind the shader, bind the texture in the vertex array, and upload your uniform data before you can draw anything. But also, within your texture, and your shader, and your renderer, after you load the data, you need to unbind it to free it from the memory for future use. So that's my basic renderer. I can input an X and Y value on my screen, a width and a height for the final rendered image, and what texture to use, and it'll render on my window. Now, to be fair, this still has a lot of bugs and it's very inefficient, so in the next couple of videos, I'll be working through those problems. But until then, I'll be updating my GitHub repository with new code every time I release a video. Go check that out if you're interested, and if you liked the video, subscribe so you don't miss new videos coming up.